Okay, the plan for today is to continue on with chapter 4, talking about 4.2, the mean value theorem, and 4.4, L'Hopital's rule. We'll push 4.3. Um, we'll kind of combine it with 4.5 and 4.6, so kind of do all the graphing stuff kind of all at once. Um, Note that the midterm exam is this week. Um, Two quick notes on that. I talked through most of this last week, but well, it's available from this morning at 9 a.m. through this coming Sunday at 11:59 p.m. I strongly recommend not waiting until the last minute to take the exam. I would strongly recommend planning to take the exam no later than Thursday night. That way, if anything goes wrong, you have kind of a full normal business day to work out anything, to get the tech sorted out. If there's a power outage or something, if you need to find an alternative arrangement, computer fails on you or something. Um, if you need to come to CCAC's campus to use internet or something, you have a lot of options available, right? If you wait until, Sunday afternoon, Sunday evening, there's not a lot of options available if something goes wrong. Note the syllabus policy, there are no due date extensions on exams. So with the exam being open for a full week, you should be able to work around, pretty much anything that comes up. But again, strongly recommend taking it or planning to take it Thursday night at the latest. And that way, if something does go wrong, you have a good bit of buffer, a good bit of margin uh, to get things sorted out. Um, the material is only going to go through 3.6. I was happy with where the exam was going up through 3.6, so we'll just keep it there. Um, the sample exam was posted, I suppose, last week. Um, and again, you can use a formula sheet, front and back of a single standard size sheet of paper with formulas, notes, anything like that on it. You can use a calculator so long as it's only a calculator, so no phones or tablets or things like that as calculators, scratch paper, and pen, pencil on the exam. One really important note is this past week, or I suppose last week at this point, um, my online Calc 3 class had their midterm exam. And for some reason, I don't understand exactly why. I think I have a suspicion why, but for some reason, the um, the password lock screen on WebAssign wasn't activating. So I had the option checked. I like triple and quadruple, checked that I had this option checked for require a password. So in theory, when they went to click to open the midterm exam, it should have come up with that password screen that if you've done the Examity practice exam, you'll have been prompted. It'll say enter password. That's where the Examity browser extension, you click on that little the yellow button with the little key symbol in it, and it enters the password for you. You submit the password on WebAssign side, and then it lets you enter the exam. That just kind of makes sure that the Examity session is up and running and everything is good to go on the Examity side before the exam starts. That's really what that's mainly for. For whatever reason, uh, for the Calc 3 folks, when they would click on midterm exam, it would just let them right into the exam without the password. I'm not sure why that is. I think it might have had something to do with the password that I chose as the password. I think the issue might have been that I used the same password for their Examity exam as for the midterm exam. That's the only thing that I can think of. Um, but anyway, so just in case it's a more widespread issue than just, me fixing that one detail, just make sure to log into Examity, get everything set up beforehand, before you go to WebAssign. It's probably even ideal to do the Examity stuff before even logging into WebAssign, get the Examity session all started up, then go over, log into WebAssign, open up the midterm exam when you're ready. And if it lets you write in, then I don't have an explanation. Maybe the password functionality is just glitchy on WebAssign right now. I've never had this happen before in years of doing this, but this was the first exam that this happened. So, but if it does let you straight in, then everything is set up and ready to go, no problems. Um, I think there might be an issue with I think the button for the enter password, when you click that, that turns into like the end proctoring session button. So, some students were having trouble ending their proctoring session. You can either just close out of the proctoring session window or whatever, whenever you're done with WebAssign, that's perfectly okay. Or I think maybe if you hit, even if you didn't need to enter the password, if you like hit the verify password button and then just say like, yes, the password thing worked okay, it might switch to the end uh, Examity session button. So again, sorry for that hassle. Ideally, hopefully, everything on the midterm exam will look just like on the Examity practice exam. But just in case it doesn't, just basically do the same process you did on the Examity practice exam, but without the password screen. That's perfectly fine. So again, log into Examity, get that set up before opening the exam, and the material will only be through 3.6. Okay, any questions on anything before we jump into things today?
Yeah, I had a question about the practice exam.
Yeah, sure.
So on WebAssign, it looks like there's two practice exam and one is password protected, one is not. Is there any like difference between them?
Yeah, yeah, so over the past couple of weeks, I've been talking about the Examity practice exam. So the Examity practice exam ideally would have been completed before this week. If not, that's okay. You can still do it this week. But that is to practice the Examity process. So that's going into Blackboard, doing the Examity sign-on, getting the account set up, going in. It doesn't really have anything to do with the academics, like are you prepared for the material for the exam or anything like that. It's really just so that you can go through the Examity process, so that you know what to expect once before the actual exam, but also to make sure that all the tech is working right, to make sure that when you try to start Examity's screen share, that like your computer will allow you to share the screen, or if you need to adjust a permission, you can do that kind of outside of the additional stress of being like, all right, I'm going to take my midterm exam coming up here, and I have to deal with all of these annoying things, first, right? So it lets you kind of practice all of the Examity stuff. So the Examity practice exam, the one that's password protected, is the one that is to practice the Examity process. Then there's the sample midterm exam that's not password protected. That is the academic side. That is like, um, if you want to know kind of what the material will be like on the exam, what the exam's going to feel like, whether you're well prepared for this material. That's the sample exam that I recommend sitting down, taking as if it were the actual exam, and um, using it as a self-assessment. So if you go through that sample midterm exam and you're happy with your score, great. You should be ready to take the midterm exam, and you should be perform well on it. If you go through the sample midterm exam and you see some deficiencies, you're not happy with your score, well, that can help direct your studying. So those are the two different exams. Note that neither of those two exams, the Examity practice exam nor the sample midterm exam, counts toward your course grade. In theory, you don't have to take either one before taking the actual exam, although I would very strongly recommend doing both of them before the actual midterm exam. The Examity one to make sure that all the tech is working right, and the sample midterm exam, even if you feel super comfortable with the material, just doing a run through of the problem types and things so that you make sure that all of the all the text boxes are working right, like everything seems to be working well on your computer, like you remember how to enter the syntax and things, for things that we haven't done in a little while. So for things like that. Yeah, so that's what those two different exams are. And then of course there's the actual midterm exam, which ideally is also password protected, but don't click on it just in case there's a wider WebAssign glitch and it doesn't come up with the password screen. Ideally, the actual midterm exam will look basically just like the Examity practice exam. You click on it, password screen comes up, and you use Examity to put in the password. But just in case, make sure to get the Examity stuff set up first before you click on the midterm exam. All right, any other questions about the exam or any of the previous content? Okay. All right. The quote of the day today is not to underestimate the impact of survivor bias when you're kind of, looking backwards for models of how to set up your life in a sense, or your strategy. Uh, this this kind of was whatever triggered in my mind whenever I over the past weekend or maybe late last week, I saw a YouTube short come up about Arnold Schwarzenegger's workout program, and I usually don't watch shorts, but every once in a while I do. I feel like if I watch too many of them, my attention span is gonna erode. But um, so basically Arnold's workout program was like for like his shoulders day was like 35 sets of shoulder exercises, and in the comments a lot of the people were like, oh yeah, I Arnold had, written books and done a movie and stuff that kind of showed what his workout program was or what he would tend to do. So people would say, hey, he's a big strong guy, I want to be a big strong guy, like I'll buy this book and kind of emulate what he does. That makes sense, right? Um, but he just did a ton of volume. And if you forget about the even the pharmaceutical help that he had, um, well, most of these people in the comments were saying, "Oh yeah, I bought Arnold's book. I tried to do his, this kind of a workout scheme, and I either just kept injuring myself or could never actually recover, or was just so systemically fatigued that I couldn't do anything else, or like basically nobody can keep up with it, right?" And so looking back, like maybe there were 1,000 people who were more or less like Arnold, genetically gifted and with pharmaceutical help and all that, but 999 of them that did this same kind of a program ended up injuring themselves or couldn't stay on it or whatever. And he was like the one out of 1,000, right? If I decide to try that program, I'm much more likely to be in the 999 that can't do it than the one like Arnold that can, right? Or the similar thing with there's a book called Rich Dad Poor Dad, great book. Robert Kiyosaki is the author, really interesting guy. I don't, this isn't a dig at him personally, but one of his kind of financial strategies, if you want to call it that, was basically like buy a whole bunch of real estate, investment real estate, get yourself into a huge amount of debt, and basically that puts a ton of pressure on you and gives you a ton of incentive to work really hard to keep your head above water, and then you'll work really hard and not be lazy and be financially successful. And that worked great for Robert Kiyosaki, right? Like, but I have a feeling that there are like 999, you know, Robert Kiyosaki clones who did the same thing and ended up like having a nervous breakdown or having to declare bankruptcy 5 times, or, like it worked great for him. And looking back, you can look at him and say, oh yeah, that was the path to success for him. But is that a likely path to success for most people, right? Look prospectively rather than retrospectively. He's kind of the survivor of the people who did that kind of crazy scheme. Not scheme, it's not like an illegal scheme, but did that crazy strategy. He's the survivor who got the huge gain, but there's a lot of failures too that we don't really see. They're not the ones writing the books. And same with Arnold. He's the survivor who won Mr. Universe and writes all the books, but the people who like, blew out their knee and, just became a personal trainer at their local gym, they don't write books. Or maybe they do, but just nobody buys them. So don't underestimate the impact of survivor bias, especially when you're looking backwards to try to determine what you should do looking forwards. Um, right. People often say like, oh, well, find a biography of somebody successful in your field and read it. That's nice for inspiration to make you get off your butt and say like, hey, I really want to do something with my life. This is really cool that I could do this, but maybe not so much for aspiration. Maybe you shouldn't like, don't, take that as a roadmap and try to go lockstep in line with what they did. Um, and this is kind of a related idea that an end result is kind of dependent on things like uncontrollable systematic effects. So like Arnold's genetics, or maybe like Robert Kiyosaki's like, family, his, parents' wealth or stability or whatever. Controllable systematic effects, which are the things we can change, Arnold's workout program or Robert Kiyosaki's financial strategy or whatever, and a good deal of chance or luck, right? Like Arnold, I mean, there are probably some people that could have been Arnold, but they just had a bad lift and blew out their back or something, and he got lucky and that didn't happen to him. Or a lot of people that could have been like Robert Kiyosaki, but they did the same strategy right before the housing market crash or something, or right before COVID hit, and just bad timing. The same strategy might have worked 5 years earlier or 5 years later, but not right when they decided to go with it. So um, these large outliers are a confluence of many tendencies, a kind of a Charlie Munger idea. Um, and we can control the controllable systematic effects. So maybe taking on a strategy that is less dependent on these two and really highlights the controllable systematic effects, where our output looks more like our input rather than being magnified up or down on the basis of things we can't control. So something to think about. Also, though, when you're young, you can take bigger risks and absorb them. You don't want to take a big financial risk when you're 65 and about to retire, but when you're young, if you want to do a Kiyosaki kind of deal, and do it when you're young, right? If you declare bankruptcy at 24, it kind of stinks, but if you declare bankruptcy at 55 and you have to move your whole family to a different, house or whatever, it's stinks a lot more, let's say. Okay, so back to chapter 4. So 4.2, the mean value theorem. And the first theorem is kind of a baby version of the mean value theorem. We'll see that the mean value theorem is a generalization of Rolle's theorem, or Rolle's is a special case of mean value theorem. That's why I didn't really want to start it in our, what do we have, 10 minutes or something left last time. So Rolle's theorem says the following. It says if these three conditions are true, if f is continuous on closed AB, if f is differentiable in open AB, and if f of A equals f of B, then there exists a C in AB and open AB such that f prime of C equals 0. So what are we kind of saying? We have an interval A to B, that's our interval under consideration. We have some function where f of A equals f of B. We need to be continuous on closed AB and differentiable on open AB. So we want to connect these two dots with a nice smooth curve. So maybe something like this. And there's my function. And Rolle's claims that there exists, it's an existence theorem in AB, or a C in AB, such that f prime of C equals 0. There exists a horizontal tangent, for instance, this one here. There could be more than one, but there will never be 0, right? So we can have more than one horizontal tangent. We could have exactly one, but there exists at least one. That's what Rolle says. The proof is actually pretty straightforward. We'll knock out an annoying case first. So let's consider the case of a constant function, just constant function. Of course, the derivative is 0 everywhere, so we could just pick wherever we want. So if we have a constant function, let's just pick the midpoint. A plus B over 2, and the derivative there is 0. We have satisfied the conclusion of Rolle's theorem. There we go. We could pick any point in the open interval A to B that we would like, and we could satisfy it that way. I feel like I got an extra space in here or something. I don't know. It just doesn't look right for some reason, but whatever. All right. The kerning just looks strange for that. So case 2 is kind of the interesting case, right? A non-constant function has to be continuous on closed AB, differentiable on open AB, and f of A equals f of B. Well, being continuous on a closed interval, and by the way, without loss of generality, let's assume that f of x is bigger than f of A for some x in AB. The other case would be f of x less than f of A for some x in AB, but it's basically the same argument. So we'll assume that f of x bigger than f of A for some x in open AB. If that wasn't the case, if f of x was equal to f of A for all x in AB, then, well, that's just the constant function. So all that this is saying is, assume we don't have a constant function. Then by the extreme value theorem, we can apply that because we have a continuous function on a closed interval. It achieves its extrema. So it attains its maximum on closed AB. Since f of A equals f of B, the maximum must be attained on the open interval AB, because there exists an output that's larger than f of A. So f of A cannot be the maximum, and neither can f of B, because f of A equals f of B by assumption 3 of Rolle's. But therefore, f has a global maximum on the open interval, and therefore a local maximum. All global maxima are also local maxima. So f has a local maximum at C in open AB. But also f is differentiable in open AB. Well, if we have a local max at a point and we're differentiable at that point, then by Fermat's theorem, f prime of C must be 0. And we've satisfied our conclusion of Rolle's theorem. So basically what we're saying for Rolle's is, let me make this maybe a little more obvious here. Say we have a clear global maximum. What we're saying with Rolle's is, for instance, if we look at the global maximum, assuming that there is an output that's bigger than f of A, if we look at the global maximum, it's also going to be a local max. And being a local max for a differentiable function means the derivative is 0. Or kind of more more in kind of the gut feeling sense, if, let me erase this, just redraw this really quick. And more the sense of like a gut feeling, if I need to get from AF of A to BF of B, if I need to connect these 2 points with a continuous smooth curve, I guess I could do a straight line, which obviously has 0 derivative. Or if I go up, well, if I go up, I have to come back down. I can't come back down like at a corner where my derivative doesn't exist, because then I want to be differentiable. So if I go up and when I come back down, my tangent lines have positive slope, come over here to negative slope. Well, at some point, they've got to have a 0 slope. And then that was the without loss of generality. We could also have functions that go like this, and then we would say there's an f of x that's less than f of A for some x in AB, and then we can do the same argument, just replacing maximum with minimum. Okay, so let's take a look at this example. Let's consider this function, f of x equals root x minus 1/3 x, on the interval 0 to 9. Let's first show that Rolle's applies here, and then let's actually find the value, or a value of C, such that f prime of C equals 0. So find the value that Rolle's theorem is kind of saying exists. Now, typically, if we were going to apply Rolle's theorem, we would do it because we don't want to explicitly find the value, but we're just kind of hitting it from both angles here, just as a demonstration. So Rolle's theorem 1 is f continuous on closed 0 to 9. And yes, it is. Note that we are right continuous at 0, and that's good enough. When we're talking about continuous on a closed interval, we mean right continuous at the left endpoint and left continuous at the right endpoint. Second, is f differentiable on open 0 to 9? And actually it is. We got to be a little careful here. F is not differentiable at 0, right? Root x is not differentiable at 0. We could either see that from the graph pretty clearly, or we know that the derivative of root x is 1 over 2 root x, and try to plug in a 0, it doesn't work. But on open 0 to 9, we're okay. And third, what is f of 0? What is f of 9? Are they equal? F of 0 pretty clearly 0, 0 minus 0. F of 9, root of 9 is 3. minus 1/3 of 9 is 3, is 0. F of A is equal to F of B. So then Rolls says that there exists a C on the interval 0 to 9 where F prime of C equals 0. Well, let's try to find it. F prime of X is 1 over 2 root X minus 1/3, and I'm curious, when is that 0? I can add 1/3 to the other side, cross multiply, I get 3 equals 2 root X, or that tells me that X equals what, 3 halves squared, or 9/4. So X equals 9/4 is a number that's between 0 and 9, and where I have my derivative being 0. Any questions on that? Okay, let's take a look at this example. Let's show that f of x equals x cubed plus e to the x has exactly one real solution. When we want to show something like this, it often comes as a two-part proof. So we often want to prove existence. We want to prove that at least one solution exists. And then uniqueness as well, proving that no other solution exists. So these are sometimes called existence and uniqueness proofs. And often we argue uniqueness using argument by contradiction. So we assume that a second distinct solution exists and then show that we get an absurd result. Or maybe we just assume that a second solution exists and show that it must be equal to the first solution, something like that. So let's show that a solution exists. Well, I do know that this is a nice function. It's a differentiable function. It's a continuous function on the whole real line. So that opens up a lot of possibilities, a lot of past theorems I can use. How can I show that a solution exists? Well, for one thing, I have my intermediate value theorem. If I can find an output of this function that's negative and another output that's positive, then I know that between those two inputs, there's got to be some input that yields an output of exactly 0. Well, has exactly one real root. Sorry. I combined two different ideas when I was typing this up. Polynomial equals 0 and having one real root. So show that function has exactly one solution does not make sense. Show that this has exactly one real root, one real x-intercept. So you're probably looking at this saying, what the heck is he talking about? Yeah, show that this function has one real root, show that polynomial equals 0 has one real solution. So let's show that a solution exists. In other words, I want to show x cubed plus e to the x equals 0 has a real solution. Well, if I take an input, probably the easiest input is 0. F of 0 is 0 cubed plus e to the 0 is 1. I see that this is greater than 0. So f of 0 is positive. Can I find an input that yields a negative number? Well, I know that e to the x is going to always be positive, but I know that x cubed, if I put in large enough negative numbers, is going to be negative. If I do like -1, what do I get? -1 cubed is -1 plus e to the -1 plus 1 over e. So -1 plus 1 over e, that is going to be less than 0. If you had used -2 or -3, no problem there either. -1 plus 1 over e. So this is like -1 plus something like 1/3, still clearly negative. This is less than 0. Also, f is continuous. So my intermediate value theorem implies that there is a solution on, what was it? -1 to 0. So we do have the existence of a solution. Now, the intermediate value theorem says nothing about how many solutions there are on the interval -1 to 0, other than that there are not 0 solutions on that interval. And it doesn't say anything about how many solutions there are to the left of -1 or to the right of 0. So we've shown existence of a solution, but not uniqueness. Who knows? Maybe if we go far enough to the left or far enough to the right of this interval, there are more solutions, or maybe even on this interval, there might be 2 or 3 solutions. Can we show uniqueness now? To uniqueness. So let's assume a second solution exists. And let's call these two solutions D and C, and they're not equal. So in other words, we have f of C equals f of D, and C is not equal to D. Actually, let me change my variable name. I use C and D for no particular reason, but let me change C to, I don't know. I guess we can use, I don't want to use E because we have E in there. I don't want to use F. Um, let's call it K. There are so many letters running around that everything has been trademarked. Rolls has kind of taken A, B, and C from us, and I want to use the C for rolls, so just so that we keep that straight. So assume that a second solution exists, so we have two solutions, and let's assume they're unique solutions, so D is not, or distinct solutions, so D is not equal to K. So we have f of K equals f of D equals 0. Both of the outputs are 0, and K is not equal to D. But I noticed that Rolle's theorem applies here. This function f is continuous and differentiable on the whole real line, so certainly on whatever interval we're interested in. Certainly on the interval between K and D. And let's, without loss of generality to make it easier to write, let's assume D less than K. So I have an interval D to K where I'm continuous on that interval. I'm differentiable in the associated open interval. That's just because this function x cubed plus e to the x is continuous and differentiable on the whole real line. So of course this is true. And I have f of d equals f of k. So by Rolle's, this implies there is c in the interval d to k such that f prime of c equals 0. But what is f prime of c? Well, f prime of c is 3x squared plus e to the x, or 3c squared, plus e to the c. But this is greater than or equal to 0, and this is strictly bigger than 0. F prime of c is strictly bigger than 0 for all real number c. So we've reached a contradiction. On one hand, Rolle's applies and implies that there has to be a c where the derivative is 0. But on the other hand, just our basic differentiation rules and properties say, and algebraic properties say that the derivative always has to be strictly positive on the whole real line. that the derivative can never be 0. If I've reached a contradiction, that must mean that some assumption that I've made is incorrect. Well, the only assumption that I made is this one here, assuming that a second unique solution exists. I keep saying second distinct solution exists. So no second distinct solution can exist. So we've now shown uniqueness as well. I assumed that a second distinct solution existed, came up with a contradiction. That would imply the derivative has to be 0 at some point, but the derivative is always strictly positive, so that cannot be the case. The only thing that we assumed was that a second distinct solution exists. So that assumption must be incorrect since it led directly to a contradiction. So no second distinct solution can exist. Our solution we found up above, or proved the existence of up above, must also be unique. Okay, so let's look at our next theorem. And Rolle's theorem is nice. The mean value theorem, though, is a generalization of Rolle's. So this is kind of a big gun theorem in calculus. It comes up often, comes up from time to time throughout the calculus sequence. So the mean value theorem, mean as in average. So like the mean of a list of numbers, it's just the average of a list of numbers. So the mean value or the average value theorem says if these two assumptions hold, f is continuous on closed AB and differentiable on open AB. So the same assumptions as assumptions 1 and 2 of Rolle's, but we've relaxed the restriction that f of a has to equal f of b. We're allowing f of a and f of b to be different numbers now. So if we're continuous and differentiable, then there exists a C and AB, so an existence proof or an existence claim, just like Rolle's, such that f prime of C equals f of b minus f of a over b minus a. In other words, what are we saying here? So in other words, I have my curve connecting AF of A to BF of B. There is a secant line connecting those 2 points. And the slope of that secant line connecting those 2 points, AF of A and BF of B, cutting through the function, is f of b minus f of a, the rise over the run, over b minus a. That's this, right? And my claim is there exists an input where the derivative at that input is equal to the slope of the secant line. The slope of the tangent line at some point along this function is equal to the slope of the secant line. Or in other words, at some point along this function, I'll have a tangent line that is parallel to this red line here, the secant line. That might occur, say, here for, say, this value of C, or it might occur here for this value of C, or maybe here for a third value of C. There could be more than one, there could be only one, but there cannot be 0 of them. I need to be able to find a tangent line that is parallel to that secant line connecting AF of A and BF of B. That's what we're saying here. We could rewrite this just by multiplying through by B minus A in a form that sometimes is more useful, that f of b minus f of a equals, so the difference in the outputs equals f prime of C times b minus a. It equals kind of a scaled difference in the inputs for a scaling factor that is the derivative at some point between a and b. this has a bit of a feel of a linear approximation, right? That differences in outputs kind of look like differences in inputs magnified by the size of the derivative. It has that kind of a feel, right? It says something slightly different. It doesn't say the same thing, but it still has that general feel. And again, note that Rolls is just a special case of mean value theorem. If I were to take mean value theorem and add on after this point, if I take this as it is, and then stick in there the requirement that f of a equals f of b, well, that just makes this numerator 0. That just makes f prime of c equals 0. And that's exactly what Rolls says. Or another way of looking at this is mean value theorem is kind of like, if you tilt your head to the left, then all of a sudden this mean value theorem just looks like Rolls, right? A slanted line, if you kind of tilt your head to the left a little bit, just looks like a horizontal line. So it's like taking Rolls and just, tilting it one way or the other. Okay, so sketch of the proof, not going through all of the details or being super precise about everything. But the idea of the sketch of the proof is let's come up with another function. We'll call it g of x. And this function is f of x, the function under consideration in the mean value theorem up here, minus this number times x. So in parentheses is a number times x. This number happens to be f of b minus f of a all over b minus a. That's what we're subtracting off of f. So if f of x minus constant times x, where that constant is the slope of that secant line here. Well, I note that g of a is f of a minus constant times a, of course, and g of b similarly. And if I compute g of b minus g of a, if I compute this, g of b, second formula minus the first, I get f of b minus f of a. So let me come over here. I get f of b minus f of a. That's these two first terms subtracted. And then I get minus. And then I have my two second terms subtracted, which is constant, which is the same in both cases, times b minus a. Right? I have constant b minus constant a. That's constant times b minus a. That whole constant just factors out. These go away. I have f of b minus f of a subtract because of this minus connecting these two terms here and here. So subtract f of b minus f of a. Well, that's just 0. So g of b minus g of a equals 0, or in other words, g of a equals g of b. It's an easier way to show it than going through all the crazy algebraic manipulations to show that g of a equals g of b. So what do we have? We have g of a equals g of b. F is continuous on closed AB, but g is only the composition of a continuous function with a linear function, which of course is continuous. We know that. So g is also a continuous function on closed AB by heavily leveraging that continuity of f. G is differentiable on open AB again because f is differentiable on open AB, and g is just f minus a linear function. So of course, the derivative of the difference is the difference of the derivatives. Again, heavily leveraging the differentiability of f on open AB. Well, hey, this looks like we should be applying Rolle's theorem to G. By Rolle's theorem, there is a C in AB such that G prime of C equals 0. But we can just compute G prime of X. Remember, f is differentiable. G prime of X is just f prime of X minus the constant, right? The constant times X differentiates to just constant. So there's the constant here, but no X anymore. And then we plug in C. G prime of C is f prime of C minus f of b minus f of a over b minus a, and that was the thing that we said should be 0 for whatever value of c in AB satisfies Rolle's theorem. Therefore, if this holds, then f prime of c has to be f of b minus f of a over b minus a. So this kind of subtracting off constant times x is what does the, in some loose sense, kind of tilting of things. It kind of tilts it back to be able to apply Rolle's theorem. So mean value theorem, very similar to Rolle's theorem. It's a generalization of Rolle's theorem. Basically does what Rolle's does without the requirement that the two outputs be the same. Okay. All right, so let's look at a theorem here. And this is a theorem that I think if I told you this, you'd probably agree without even seeing a proof. It seems kind of obvious, but it does require a formal proof. The theorem is if f prime of x equals 0 for all x in AB, then f is constant on AB. If the tangent line is horizontal at every point in an open interval, then f is constant on that whole open interval. Okay, so let's go through the proof of this. The proof of this actually is a little bit tricky and a little bit nuanced. Like our first, what it feels like we should do at first is to say something like consider AB and go from there. But I have two problems with that. Well, my first problem is if I want to use something like the mean value theorem or Rolle's theorem or any of those, I actually don't know if f is continuous on closed AB. My theorem only said if f prime equals 0 for x in the open interval. It could be discontinuous at A or at B. So I actually don't quite have enough of an assumption to apply mean value theorem or Rolle's because I don't know about the continuity on the closed interval. Now you might say, okay, well, let's just change the statement of the theorem so that it's like applying to a closed interval or something. Maybe we could get away with that. I don't know. That also brings up some other points of contention, but the bigger problem is let's just assume that, let's assume for sake of argument that this is okay, that we somehow magically know, we add in an assumption, if f prime is 0 on open AB and f is continuous on the whole real line. Okay, so now we can apply mean value theorem, Rolle's theorem, we've kind of satisfied that. But what I might want to do is to show something like, f of b minus f of a equals f prime of c times b minus a. Show that this is 0. Show that since this is 0, f of b has to equal f of a. This is kind of what it feels like I want to do from the mean value theorem. But my problem is that it kind of even forgetting about the issue with these endpoints and not being able to apply the theorems, if I magically fix that somehow with a much stronger assumption, all that I've really done is shown that the endpoints have to be the same. I've said nothing about the interior of A to B, which is the whole point of interest here, right? So there's actually a bit of a nuance to a problem like this. I think instead of undoing, I'm just going to erase. There's a bit of a nuance to something like this. So what does it mean for a function to be constant on an interval? It means if, say, x and y are in the interval AB, then f of x equals x of y, f equals f of y. In other words, I need to make a statement about every pairing of points in this open interval. Every pairing of inputs yields the same output for both of those inputs. That's really what it means. So I actually need to deal with two arbitrary inputs. So right, this is what f being constant on interval means. Well, so it kind of seems like I should then consider some interval being a subset of the open interval AB. I guess, at this point, it wouldn't be a wrong statement to choose an open interval. But I kind of, thought a little bit through the strategy before, and I want to leverage this zero derivative here along with something that looks like this, where I can make two function outputs equal, the two function outputs difference equals 0. So I want to apply mean value theorem. I need a closed interval. So instead of an open interval, I'll just choose a closed interval to deal with. So let's let closed interval x to y be a subinterval of open interval a to b. So I have a to b here, and I pick some closed interval that's a subinterval. So everything that I know about f that's on open AB also applies to f on xy, on closed xy. Maybe not quite everything that I know about f, but the relevant things that we're concerned with here. So let closed xy be a subinterval of open AB. And we're leaving this arbitrary. These could be chosen any way we want. I guess y has to be bigger than x, but other than that, these are two arbitrary inputs in the open interval AB. Then I know that, well, f is, of course, differentiable on open AB. Let's say f is differentiable on open xy because it's differentiable at every point in AB. And actually now I pick up that continuity. X, the endpoint x, is a point that is strictly between A and B, as is the endpoint y. I pick up the continuity at the endpoints because I'm using a subinterval. F is continuous on closed x to y. And of course, every point in between, it's continuous as well because those are also points in AB. So I now have an interval closed x to y over which my function f is continuous on the closed interval and differentiable on the open interval. So the mean value theorem applies here. I suppose the mean value theorem always applies, but really what I mean is the conclusion of the mean value theorem applies. So this says that f of y minus f of x equals f prime of c times y minus x for some c in, well, in the interval x to y. But I know if c is in the interval, the open interval x to y, it's certainly in open AB. Therefore, f prime of x has to be 0 because, or sorry, f prime of c has to be 0 because f prime of x is 0 on the whole interval open AB. So this tells me that f of y minus f of x equals 0, right? This is 0, which says that f of y equals f of x. So for an arbitrary x and y in the open interval AB, f of y equals f of x. That is the definition of f being a constant function. If x and y are in the interval, their outputs are the same. Therefore, f is constant on AB. So even a pretty simple theorem like this that feels like it's almost like right there, we just have to be a little careful, right? We had to come up with this idea to like construct a subinterval that was a closed interval so that I could apply mean value theorem, and the details kind of worked out nicely. Everything worked out well. I wasn't just saying something about the endpoints. I wasn't sticking myself in a situation where my assumption isn't quite strong enough, right? So by choosing this subinterval, this closed subinterval, that made everything work out just right. Corollary to this, let me zoom in here just a little bit. Corollary to this is if two functions' derivatives match, if f prime of x equals g prime of x for all x in open AB, then the functions differ by only a constant term on open AB. F of x equals g of x plus k, a constant on open AB. And the proof is pretty straightforward. We take h of x to be the difference, f of x minus g of x, and apply our previous theorem to h, right? We would then conclude that f minus g, if the derivatives are equal, f prime minus g prime, well, that's h prime, is 0. Then the difference between the functions, so, right, if h prime is 0, then h has to be constant. If the difference if the derivative of the difference is 0, then the difference must be constant. And there we go. We just apply the previous theorem to this choice of h. So if two functions' derivatives match, the functions are the same, but up to a constant term. This is something that we, maybe, in not so formal of a way, kind of intuited or kind of gave evidence for way back in chapter 2. That derivatives matching really only means that the functions are the same up to a constant term added on. And now we see that formally proved very carefully here. Okay, let's look at this next example. Let's prove that the absolute value of sine x minus sine y is less than or equal to absolute value of x minus y. Well, if we look, let me just actually pull this down. If we look at the conclusion of mean value theorem, really one of the big basically the big crux of it is this statement here, that the difference in outputs is related to difference in inputs through the derivative, roughly speaking, right? Kind of the same idea as linear approximation, difference in outputs being related to difference in inputs through the derivative. The linear approximation basically said if I take my anchor point for my derivative to be, say, a by f prime of a, then I have to make this an approximate sign. And the mean value theorem says I can make this an exact equal sign if I let my point where I take the derivative kind of float, right? If I get to choose, if I get that degree of freedom to choose where I take the derivative, then I can gain exact equality between these two sides. Well, this looks a lot like that, right? I have something that's like difference in outputs being related somehow to the difference in inputs. That structure relating differences in outputs to differences in inputs is what really keys my brain into something like mean value theorem, uh, the conclusion that I see down here. Now, of course, I have absolute values here. Does that really change much? Not really. I can just slap absolute values here, here, and here. That doesn't really change much. So let's try to go to work on this. Let's consider the interval. let me do y to x. It doesn't matter, but I'm just going to do it this way so that we don't have to, there'll be one less step of switching things around. So let's consider the interval, closed interval, y to x. Clearly this is a closed interval on the real line. And let me consider a function f of x equals f of z equals sine z. I keep backing myself into a corner with my choices of variables, and so maybe I should have chosen like, well, I can't choose a to b either because that's already kind of like trademarked by the mean value theorem. So f of z equals sine z. And we know that f is differentiable on open y to x and continuous on closed y to x. That's a property of the sine function. So my mean value theorem says there is a c in the interval open interval y to x such that, well, what do we have? F of x minus f of y equals f prime of c times x minus y, or sine x minus sine y equals something times x minus y. What is f prime of c? Well, that's just cos of c. Okay, so I'm getting pretty close. I don't have my absolute values on here yet. I don't have an inequality yet. And I do still have a cosine of c on the right-hand side. I haven't gotten rid of that yet. So I think if two sides are equal to one another, I can just put absolute values on them and it's still equal. So that shouldn't be too bad. So I have my absolute values on. Now I have an absolute value of cosine of c on the right-hand side. I want to get rid of that. And I expect my equals to turn into an inequality. Well, I know that absolute value of cosine of c is in the interval, the closed interval 0 to 1. I also know that absolute value of x minus y is positive. And I guess, do I want to require that x be strictly bigger than y or not? I guess, we can maybe make this a little more general by actually even allowing x to be y. Of course, if x equals y, then we have 0 less than or equal to 0, which would also be valid. So we'll say that this is bigger than or equal to 0. But if I have a number between 0 and 1 multiplied by a positive number, if I increase that factor, then the whole thing just gets bigger. So this would be less than or equal to absolute value of x minus y. If I replace absolute cos of c, which could be anything between 0 and 1 inclusive, if I replace that with 1, it's multiplying a positive number, so the factor gets larger and the thing it's multiplying is positive, so the whole thing gets larger. I do have to be really careful with the sign here, sign sign. If I have something that's multiplying a negative, if I made it bigger, it would be more negative. That would actually be less, it would go the other direction, right? Like if you double the amount of money in your bank account, if you have positive money, that's good. If you have negative money, then you have less money. So I can't just think that if I increase a multiplicative factor, that always pushes the whole thing to the right. If I increase a multiplicative factor, it depends on the sign of the stuff that it's multiplying. But here, because of the absolute values, the stuff it's multiplying is always non-negative. So we can definitely do this. I couldn't do that at this step though, right? Unless I had imposed, that x bigger than y or something like that. I would have to be more careful with my sign and SIGN and all of that. Or yeah, x bigger than y. So I had to be a little more careful with making the argument that x minus y has to be non-negative and being careful with that. But here, since it's in absolute values, I didn't have to worry about it, even though x minus y is still non-negative because of the way we set up our interval up here. So this interval implies x bigger than y. But we don't want to be too flippant about just saying if we increase a factor, that always increases the output. That's not always the case. Okay, so what did we show then? For an arbitrary interval y to x, closed interval in the real line, absolute sine x minus sine y, less than or equal to absolute x minus y. And that's exactly what we wanted to show here. Does it matter that we started with an interval? Not really. It's just that we chose this interval to be so that the endpoints were the points of interest that we were working with, the arbitrary values y and x. And that's what got us our conclusion. Any questions on this one? All right, and a little side note, this is just kind of like a fun little application of mean value theorem. If we have a function f of t representing distance as a function of time, so for instance, if you're driving in your car and you go a certain distance and it takes you a certain time to go that distance, that's what f of t is. And if t minimum is the time it takes to cover x distance, a certain distance, at a given speed, say for instance the speed limit, we'll also assume that f is continuous, that you can't change distance discontinuously. If you like entered a wormhole and warped ahead, 200 feet and came out of the wormhole instantly 200 feet ahead, well, the conclusions don't apply. But the mean value theorem says that if you cover x distance in t naught time, where t naught is a time less than t minimum, at some point your speed was above the given speed used to calculate t min based on that distance. Or another way of saying it is, if your average speed over a certain time or over a certain distance was over the speed limit, then at some point you were traveling over the speed limit. Now, we don't know how fast you were traveling, right? You might have been, if the speed limit was 25 miles an hour, you might have been going 26 miles an hour for a while, and then 40 miles an hour, you sped up really fast and then saw the cop and slammed your brakes and came down to 15. Or you might have been going 10 all the way across and then like gunned it, went up to 40 and came back down and back down to 10. Or you might have been going, 27 most of the time. So we don't know, what your max speed was, but we know that it was over the speed limit. And really, we know that it was over kind of the average speed over that time period. So we don't know what the max speed was. We only know the minimum possible maximum speed. We know that your maximum speed was at least as fast as your average speed. Note that kind of the opposite conclusion isn't really informative in this example. If we computed your average speed and it was below the speed limit, you might have been traveling below the speed limit the whole time. If I said your average speed, the time it took, based on the time it took you to cover this distance, your average speed was 23 miles an hour to 25. You might have been going 23 the whole time, or between 22 and 24 the whole time. You might have been going 15, sped up to 60, slammed the brakes, came back down to 15, and so you weren't necessarily traveling below the speed limit the whole time just because your average speed was lower than the speed limit. But if your average speed is higher than the speed limit, you have to have been traveling above the speed limit at some point in that interval. Note that the opposite would say that if your average speed was below the speed limit at some point, you had to have been traveling below the speed limit. But for like writing tickets or getting you in trouble, that's not a, you know, that's not a um, point of evidence. Any questions on the mean value theorem? Okay, so let's jump into 4.4 then, L'Hopital's rule. We're going to cover this before we cover graphing, and then we'll kind of lump the three graphing sections all together. So let's look at a motivating example here. Let's compute limit x goes to 0 from above of x times log x. So this x is kind of trying to go to 0, but this log x, as x goes to 0 from above, it's kind of trying to go to minus infinity. We have something that's like a 0 times a minus infinity. This is an indeterminate form. And we've seen these indeterminate forms a lot before. All of our derivatives involves indeterminate forms. So something like a 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, things like this. So these are indeterminate forms where there's kind of a battle. I suppose also like a 0 to the 0 power, although people argue about this. Right. So what's the kind of gut feeling, the non-mathy idea in an indeterminate form? It's like there's two countervailing powers. This numerator wants to take me to 0. This divided by 0 wants to take me to something that kind of feels like an infinity, right? 1 over 0 feels like infinity. 0 over 1 feels like 0. So I'm getting pulled in two different directions. The numerator going to infinity wants to make my output large. The denominator going to infinity wants to make it small. The first term going to plus infinity wants to make me large positive. The one going to negative infinity wants to make me large negative. They're kind of tugging war. Maybe the plus infinity wins out, maybe the minus infinity wins out, maybe they meet in the middle. 0 times infinity, the 0 times anything, something like 0 times anything is 0, but infinity times anything is infinity. The 0 wants to bring everything to 0, the infinity wants to pull everything up to infinity. 0 to the power is 0, well, 0 to any power is 0, but anything to the 0 power is 1. Again, there's a bit of a countervailing forces here. So this is kind of the gut feeling, right? If we have two different components, that if I look at each one of them individually, one of them wants to kind of do one thing and one of them wants to do the other thing, and there's a tug of war, there's a disagreement there, right? If I have something like infinity plus infinity, well, that just goes to infinity, probably, as long as things kind of don't explode or something. Or like if I have like an infinity over 0, that probably goes to infinity, speaking very loosely here. Yeah, right. So these are cases where there's not really a disagreement between the different terms or the different factors or whatever. Um, yeah, put this in big quotes. These are very rough kind of, ideas here. So L'Hopital's rule is it's a tool to help us deal with these limits of indeterminate forms. So L'Hopital's rule says the following: let's let R of x equals P of x over Q of x. So we could think of this as like a rational expression, polynomial over polynomial, but it doesn't have to be, right? It typically can be just the ratio of two functions. If either A is true, or if A either the limit of the numerator and the limit of the denominator both are 0. So basically, if I have an indeterminate form of type 0 over 0, or if the limit of the numerator goes to plus or minus infinity and the limit of the denominator also goes to plus or minus infinity, they don't have to be the same sign. If I have a indeterminate form that looks like this, and also if both of the derivatives exist near A, near the limiting point, then I can say the following. I can say limit x goes to r of x, in other words, just limit x goes to ap of x over q of x. The limit of that ratio of these two functions, p and q, is the same. I can write equals limit of the ratio of their derivatives. Note the real strangeness of this. This is a very strange thing. This isn't something we would expect. It's not like we compute the derivative of r. It's not like we take r prime, which would be a big quotient rule kind of thing with a q squared on the bottom and everything. And that's not what we're doing. We have a numerator function and a denominator function. We take each of their derivatives separately, and then we take the ratio of their derivatives. Very strange thing to do, right? This isn't like, it's not like we're computing the limit of r prime or something instead of r. We're breaking r into its numerator and denominator components, and if they satisfy these criteria, then we're taking the limit of the derivative of the numerator over derivative of the denominator. That's one of the big mistakes students make, is they take the derivative of the whole fraction and find like r prime with the quotient rule and all that, but not only is that incorrect, but this result is actually a lot simpler computationally than doing all of that. And that's actually kind of the whole point of doing this, is that often taking derivatives of functions makes them simpler to work with. The other important note is we can't just L'Hopital any limit that's a ratio of two functions, right? If I just see limit x goes to a of function of x over function of x, I can't just decide, well, I'd rather work with the ratio of the derivatives. And well, no, it has to be one of these indeterminate forms, like a 0 over 0, infinity over infinity type of indeterminate form, and the derivatives have to exist near A. So don't overcomplicate it, but also don't try to apply it all over the place, right? So don't go into the midterm, and anytime that you see from chapter 2 the limit of some ratio of functions, like don't immediately L'Hopital it and just assume you can. You can only hit it with L'Hopital's rule if it is one of these types of indeterminate forms. All right, let's look at an example. Limit x goes to 0, sine x over x. So here I have r of x, the ratio is p of x over q of x sine x over x. And I do note that p of x does go to 0 as x goes to 0, and q of x also goes to 0 as x goes to 0. Requirement A of the assumptions for L'Hopital is valid. I have a 0 over 0 type limit. Requirement B, do the derivatives exist near 0? Yeah, sure. Sine x and x are both differentiable in the whole real line, no problems at 0. So the assumptions for L'Hopital have been satisfied. Now I can apply the conclusion. And remember that the conclusion deals with p prime and q prime, their ratio. So let me differentiate them separately. The derivative of p is cos x, the derivative of q is just 1. And then I can say this limit equals limit x goes to 0 of p prime over q prime, cos x over 1. Well, this is actually a super easy limit to do. Limit x goes to 0 of cosine of x. Cosine is nice and continuous at 0. That's just cos of 0. That's just 1. So it turns out the limit of this ratio is 1. And we might actually think back to section 4.3 and realize that, hey, this was kind of the whole reason we couldn't just compute the derivative of sine x just from the limit definition. We ran into this limit and one other, but the other limit's pretty similar to this one in nature. Could we have saved ourselves that whole hassle of a geometric argument by just doing this, by doing this in 2 lines? Well, the answer is no, because, well, I needed to know the derivative of sine x to be able to L'Hopital it, right? So the answer is no, I couldn't have just directly used this result to evaluate this limit way back then, because I was figuring out what the derivative of sine x was, and I would need to use it here. I would need to use what I was trying to prove in order to prove it, so that wouldn't have worked. So that would have been circular logic. At best, that would have done something like prove that the derivative of sine x could be cos x, but maybe it's not. So it would prove that there's maybe not an internal inconsistency, but wouldn't have it wouldn't have gotten rid of the need for another proof. Okay, let's revisit this one from above then. I do have a bit of an issue here. Limit x goes 0 from above of x log x is kind of like a 0 times infinity indeterminate form, not a 0 over 0 or infinity over infinity. So at first glance, we say, I can't use L'Hopital's on this. Maybe I have to use some other method or something. I don't know. But I can't be a little bit creative. I know that a zero is kind of like 1 over infinity, right? If I have a fraction that's like 1 over a really big number, that's like an output that's pretty close to 0. So a 0 times infinity, kind of like infinity over infinity. Can I manipulate this to make that happen? Well, instead of x in front here, maybe if I write x as 1 over x. I mean, it seems like kind of a silly thing to do, except that now, as x goes to 0, log x, as x goes to 0 from above, log x goes to negative infinity, and 1 over x goes to positive infinity. And now we do have numerator and denominator each going to one of the infinities. And the derivatives exist in some open interval around a, maybe not to the left of a, but some like open interval to the right of 0. So this is my p of x. And this 1 over x is my q of x. So what's p prime of x? 1 over x. What's q prime of x? Well, 1 over x, the derivative of that, x to the minus 1, is negative x to the minus 2. And now by L'Hopital's, I usually write a little like LH there above the equal sign so that it's kind of clear what's going on, because this is such a strange, um, change to make. So we do p prime over q prime, or 1 over x, divided by negative 1 over x squared. Well, that's limit x goes to 0 from above of, well, this negative x squared on the bottom comes up as a negative x squared over x, or just a negative x. And of course, that's 0. So limit x goes to 0 from above of x log x is 0. Any questions so far? Okay, as an exercise, prove that if f prime is continuous, this limit equals f prime of x. What is this limit? This is kind of like if we had chosen to set up our derivative using a secant line that goes a little bit to the right and a little bit to the left. Right. So if I go h to the right and h to the left, the slope of the secant line is going to be f of x plus h minus f of x minus h all over this run, so to speak, of 2h. Seems like a sensible thing to do. Do we get the same derivative if we set things up this way? And the answer is yes, we do. And we can prove that here. We'll work through a pretty similar example. And this deals with the second derivative. We actually never really introduced any way to compute the second derivative directly. We said, well, just compute the first derivative, then you get a new function and compute its derivative. So we did two first derivatives, but we have a limit here that we're saying is a direct way to compute the second derivative. So we take f of x plus h plus f of x minus h minus 2f of x. So it's kind of like this right endpoint plus the left endpoint minus 2 over the middle over h squared. And the claim is that we take the limit h goes to 0 of this. That gives us f double prime of x. Let's see if that's true. One thing I want to be careful about here, I'll write it in red. The limits variable is h. So when we're talking about L'Hopital up here, x goes to a, and we're taking p prime of x and q prime of x. These are derivatives with respect to x. These are derivatives with respect to the variable in the limit. When we take derivatives here, we're going to be taking d by dh, not d by dx. X is the dummy variable. It's the input into our derivative. It's our location of interest. The variable of interest as far as L'Hopital is concerned is h. So I do want to be careful about that, both in this example and the same comment applies up here. So when I take derivatives, I'm not going to be taking d by dx, I'm going to be taking d by dh. All right, so let's take a look at this. Well, I do have limit h goes to 0 of the ratio of two functions of h. This is, say, p of h, and this is q of h. Well, p of h, as h goes to 0, p of h goes to f of x. F is twice differentiable. Its first derivative is continuous. It's certainly first differentiable. It's the function itself is continuous then, right? So the differentiability implies the underlying continuity, so we can just pop our h's into there as needed. We get f of x minus 2f of x plus f of x minus 0, or just f of x. That is 0 that p of h goes to, sorry. Q of h is h squared, which of course goes to 0 as well as h goes to 0. So my numerator and denominator both go to 0. I have a 0 over 0 type indeterminate form. Now let me be careful here. Let me consider p prime of h. By that I mean dp by dh. Let me write it that way because I know I'll mess it up if I don't otherwise. So f of x plus h. Well, this is like f of u, right? That's df du du dh. That's f prime of x plus h times d by dh of the inside. X is constant in terms of h. D by dh of h is just 1. So that's all I get out of there. minus 2f of x, well, in h, that's just a constant. If I differentiate with respect to h, that minus 2f of x goes to 0. Maybe I'll write it in here, minus 0, or say plus 0, just as a reminder. And then I differentiate this last one with respect to h, and I get f prime of x minus h. But here, if I did like v equals x minus h, I did df dv dv dh. But dv dh now is the derivative of negative h, that's minus 1. And then dq dh is much easier. It is 2h. And hey, look at what I get out of here. So by L'Hopital's, this limit is the limit, h goes to 0, of dpdh over dqdh, f prime of x plus h minus f prime of x minus h over 2h. And that limit looks kind of familiar. That's this limit. That says whatever function I'm dealing with as my f input into the limit, I take its derivative as the output. So this is f prime prime, or f double prime of x. So I can cheat and use this exercise here. So you can kind of, basically I did one application of L'Hopital to get down one derivative. And, this exercise is basically just using the second application of L'Hopital to get down the remaining derivative. Any questions so far? All right. The next problem I want to do is deals with the area of a circle, computing the area of a circle. Kind of ironically, you've probably gotten to calculus and you've probably known the area of a circle is pi r squared for, I don't know, since like fourth grade or fifth grade. I don't know when they cover it, but it's probably never been proven to you. Somebody just told you this is the area of a circle and you read it in a bunch of books and who knows why. Well, we're actually going to prove the formula for the area of a circle next time. And we'll see that it uses L'Hopital's rule, computing limits, some other interesting ideas. So we don't have enough time to work through it today. So in the last 7 minutes or so, we'll leave that till next time, but computing the area of a circle next time. And then we'll do one last limit next time. We'll probably do this one first as like just a refresher, warm up on L'Hopital, and then knock out the area of a circle. And we'll have proven something that you've probably used for, I don't know, however long it's been, 15 years or 10 years or something. All right, any questions on anything from today about the exam?